Right now, as you watch this video, the Andromeda galaxy is racing toward us at 250,000 miles per hour. In 4.5 billion years, it will collide with our Milky Way in the most spectacular cosmic event our galaxy has ever experienced. But here's what makes this collision truly mind-bending. Despite Andromeda being our nearest galactic neighbor, despite it being visible to the naked eye on clear nights, and despite having 4.5 billion years to prepare, it is absolutely impossible for humanity to travel there before the collision occurs. Not difficult, not challenging, impossible. The word impossible gets thrown around callously in our everyday lives. Impossible to finish that project by deadline. Impossible to understand quantum mechanics. Impossible to find parking downtown. But when physicists use the word impossible to describe intergalactic travel, they mean something far more fundamental and terrifying. They mean that the basic structure of reality, the expansion of space itself, the finite speed of light, the energy requirements dictated by Einstein's equations, makes traveling to another galaxy as impossible as traveling to yesterday or making 2 + 2 = 5. The numbers alone are staggering. Andromeda lies 2.5 million light-years away. That means light, the fastest possible thing in the universe, takes 2.5 million years to cross the void between our galaxies. A photon that left Andromeda when early humans were just learning to use stone tools is only arriving at Earth today. If we could somehow travel at 99.9% the speed of light, a velocity that would require more energy than our sun produces in millions of years, the journey would still take over 2.5 million years as measured by outside observers. But the situation is far worse than these crushing distances suggest. The space between galaxies isn't static. It's expanding, not just spreading apart like debris from an explosion, but actually growing larger at every point. The void between us and Andromeda is literally manufacturing new space every second, making the journey longer even as we travel. It is like trying to walk across a treadmill that is accelerating backward faster than you can run forward. Dr. Lawrence Krauss, the renowned cosmologist, describes intergalactic travel as not just impractical, but fundamentally prohibited by the structure of spacetime itself. The universe has built-in barriers that make escaping our cosmic neighborhood as impossible as breaking the laws of thermodynamics or exceeding the speed of light. These aren't technological challenges waiting for clever engineering solutions. They're absolute limits imposed by reality itself. Consider what this means for our cosmic perspective. Earth orbits a star that orbits within a galaxy containing 400 billion other stars, surrounded by trillions of other galaxies scattered across an observable universe 93 billion light-years in diameter. Yet despite this vast cosmic wealth, despite the mathematical certainty that countless other worlds harbor life and intelligence, we are forever trapped within our single galactic island, isolated by distances so enormous they mock our every attempt to comprehend them. The implications extend far beyond space travel dreams. If intelligent civilizations arise throughout the cosmos, as mathematics strongly suggests, then each remains forever isolated in its own galactic prison. The universe has created a cosmic archipelago where islands of consciousness can never contact each other, where the most profound questions about life, intelligence, and meaning must be answered in permanent solitude. Recent observations have made this isolation even more crushing. The Hubble Space Telescope has revealed that the expansion of space is accelerating, driven by mysterious dark energy that comprises 68% of the universe. This acceleration means that galaxies beyond our local group, the small cluster containing the Milky Way, Andromeda, and about 80 smaller galaxies, are moving away from us faster and faster. Distant galaxies are receding at velocities approaching the speed of light, meaning they're disappearing beyond our ability to ever reach them, even with perfect technology. This creates what cosmologists call the Cosmic horizon, a boundary beyond which objects are receding so rapidly that light will never have time to travel between them. As time progresses, this horizon shrinks, gradually cutting us off from more and more of the universe. We exist during a brief cosmic moment when we can still observe distant galaxies. Future civilizations will inherit a universe where most galaxies have disappeared beyond the cosmic horizon, leaving them in an apparently empty cosmos with no evidence that other galaxies ever existed. But even within our local group, that small collection of gravitationally bound galaxies that won't be carried away by cosmic expansion, the distances remain impossibly vast. The nearest major galaxy beyond Andromeda is the Triangulum galaxy at 3 million light-years. The nearest galaxy cluster is the Virgo cluster at 50 million light-years. These distances represent barriers so absolute that they make the difference between walking to the corner store and walking to the moon seem trivial. If you're refascinated by the ultimate limits of human exploration and want to understand why the universe designed itself to keep civilizations forever isolated, subscribe and hit thumbs up. And here is a question that will haunt your dreams. If every intelligent species in the cosmos faces these same impossible barriers, does this mean consciousness is destined to exist in eternal cosmic loneliness? Comment below with your thoughts on whether intelligence throughout the universe is doomed to permanent isolation. What we're about to explore goes beyond the engineering challenges of building faster rockets or developing new propulsion technologies. We're reinvestigating the fundamental structure of reality itself, why the universe operates by rules that make some dreams not just difficult to achieve, but logically impossible. We'll discover how space expansion, time dilation, energy requirements, and basic physics conspire to create an absolute barrier around every galaxy in the cosmos. The journey ahead will take us through Einstein's insights about spacetime, through the mind-bending mathematics of cosmic expansion, through energy calculations that dwarf the total output of stars, and through time dilation effects that make the very concept of intergalactic travel meaningless for conscious beings. We'll explore why even theoretical technologies like warp drives and wormholes fail to solve the fundamental problems, and why the universe seems designed to keep every island of consciousness forever isolated. This isn't a story about technological limitations or engineering challenges. It's a confrontation with the deepest truths about reality itself. The universe has written laws that confine every thinking species to its galactic birthplace, ensuring that the vast cosmos remains forever mysterious, forever unreachable, forever beyond our grasp. By the end of tonight's exploration, you will all understand why physicists speak of intergalactic travel not as a distant dream, but as a fundamental impossibility. More importantly, you'll grasp what this cosmic isolation means for humanity's future, our search for meaning, and our place in a universe that is simultaneously infinite in scope and absolutely limited in accessibility. The barriers we're about to examine aren't waiting for future technology to overcome them. They're woven into the fabric of spacetime itself, as permanent and unchangeable as the laws of mathematics. Understanding these barriers reveals something profound about the nature of existence in a cosmos designed for beauty, wonder, and eternal mystery, rather than conquest and exploration. Now, let us begin our investigation into why every galaxy in the universe exists as an island of permanent cosmic isolation, and what this means for consciousness throughout the cosmos. Chapter 1. Impossible Distance. The first and most overwhelming barrier to intergalactic travel is the sheer, incomprehensible scale of the distances involved. When we say Andromeda is 2.5 million light-years away, we're using numbers so large they transcend human ability to truly comprehend them. These aren't just big numbers. They represent distances so vast they exist beyond the reach of human intuition, beyond our capacity for meaningful visualization, beyond the scope of any earthly comparison. To understand how impossible these distances are, Let's start with something familiar and scale upward. If Earth were reduced to the size of a marble, the Moon would be a pea located 30 marble diameters away. On this scale, the Sun would be a sphere 16 feet across positioned half a mile from our marble Earth. Pluto's orbit would extend 20 miles in every direction. These solar system distances already stretch our ability to visualize, but they're nothing compared to galactic scales. On our marble Earth scale, the nearest star to our Sun would be located 125,000 miles away, halfway to the actual Moon. Our entire galaxy would span 100 million miles, roughly the distance from Earth to the Sun in real life. And on this scale, where our galaxy stretches across 100 million miles, the Andromeda galaxy would be 2.5 billion miles away. The distances between galaxies are so enormous they dwarf even the scale of galaxies themselves. Dr. Neil deGrasse Tyson often illustrates these scales by noting that if you could travel at the speed of a commercial airliner, about 500 miles per hour, it would take you 9 million years just to reach the Sun. At the same speed, reaching the nearest star would require 5 billion years. Crossing our galaxy would take 5 trillion years, and reaching Andromeda would require 13.5 quintillion years, a number larger than the age of the universe multiplied by itself a billion times. But even these calculations understate the problem because they assume travel through static space. The reality is far worse. The space between galaxies is an empty void waiting to be crossed. It's actively expanding, creating new distance faster than any realistic spacecraft could traverse it. Imagine trying to swim across a river that's growing wider every second. Even if you're a strong swimmer, if the river expands faster than you can swim, you'll never reach the other side. Recent measurements by the Planck satellite have determined that space expands at approximately 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, space grows by 70 kilometers every second. At Andromeda's distance, the space between us and our neighboring galaxy is expanding at about 54 kilometers per second, roughly 120,000 miles per hour. The void itself is racing away from us at speeds that would make our fastest rockets look stationary. This expansion creates what cosmologists call recession velocity, the speed at which distant objects move away from us due to the expansion of space itself. Objects aren't moving through space. Space itself is carrying them away. It is the difference between walking backward on a moving sidewalk versus having the sidewalk stretch longer beneath your feet as you walk. In cosmic expansion, new space materializes between every point, making journeys longer even as you travel. The mathematics becomes truly disturbing when you calculate the vart, moving distance to Andromeda, the distance accounting for cosmic expansion during a hypothetical journey. Even if we could travel at a significant fraction of light speed, the expansion of space would continuously increase our destination distance. A journey that starts at 2.5 million light-years becomes longer every moment of travel. It's like chasing a horizon that retreats faster than you can approach it. Dr. Sean Carroll's calculations show that for galaxies beyond our local group, the recession velocity equals or exceeds any realistic travel velocity. This creates what physicists call the Hubble sphere, a boundary beyond which galaxies recede faster than light speed due to space expansion. Objects beyond this boundary become causally disconnected from us. No signal, no spacecraft, no information can ever travel between causally disconnected regions. The local group, our small cluster of about 80 galaxies gravitationally bound together, represents our cosmic neighborhood, the only region where space expansion doesn't dominate over gravitational attraction. Within this group, galaxies can theoretically be reached because they're not being carried away by cosmic expansion. But even here, the distances remain staggering. The Triangulum Galaxy, the third largest galaxy in our local group, lies 3 million light-years away. To put this in perspective, consider human timescales. Recorded human history spans about 5,000 years. Human civilization as we know it has existed for perhaps 10,000 years. Homo sapiens has existed for roughly 200,000 years. Yet the light we see from Andromeda tonight left that galaxy 2.5 million years ago, more than 10 times longer than our species has existed. By the time light travels between local group galaxies, entire species rise and fall. Ice ages come and go. Continents drift across planetary surfaces. The psychological impact of these distances is profound. Every galaxy we see in the night sky, those faint smudges of light that represent hundreds of billions of stars, exists in the deep past. The Andromeda galaxy we observe tonight shows us how it appeared when our early ancestors were learning to use fire. More distant galaxies show us increasingly ancient cosmic history. When we look at galaxies billions of light years away, we see them as they existed when the universe was young, when the first stars were forming, when cosmic history was just beginning. This temporal displacement means that intergalactic travel involves not just crossing space, but crossing time. A journey to Andromeda wouldn't just take millions of years. It would arrive at a destination that had evolved and changed beyond recognition during the journey. The galaxy you aimed for at the beginning of your trip would be a different galaxy entirely by the time you arrived. Stars would have been born and died. Stellar orbits would have shifted. Even the galaxy's overall structure might have transformed through interactions with other nearby galaxies. Recent computer simulations of galactic evolution reveal how dramatically galaxies change over millions of years. Star formation rates fluctuate, spiral arms develop and dissolve, supermassive black holes grow and affect surrounding stellar populations. The Andromeda galaxy that exists today will be fundamentally different from the Andromeda galaxy that exists in 2.5 million years when hypothetical travelers might arrive. This temporal aspect creates a philosophical paradox about the very meaning of intergalactic travel. If the destination changes completely during the journey, in what sense are you traveling to that destination? It's like trying to visit a city that gets completely rebuilt every day during your journey. By the time you arrive, nothing you intended to see would still exist. The scale problem extends beyond distance to encompass energy, time, resources, and fundamental physics. These are engineering challenges waiting for better technology. They reach absolute limits imposed by the structure of spacetime itself. The distances between galaxies exist at a scale where normal concepts of travel, journey, and destination lose their meaning. Even theoretical perfect technologies run against these distance barriers. Suppose we could build spacecraft that approach the speed of light with perfect efficiency, requiring no fuel, suffering no mechanical failures, operating for unlimited time periods. Even with such impossible technology, the journey to Andromeda would require 2.5 million years. No human civilization has ever lasted even a tiny fraction of that time. No species remains unchanged across such temporal scales. The concept of us traveling anywhere becomes meaningless across these time periods. The expanding space between galaxies creates an additional layer of impossibility. As cosmic expansion accelerates due to dark energy, the effective distance to other galaxies continues growing even for objects within our local group. Future space travelers would face target destinations that are literally moving away from them faster and faster, creating journey distances that increase exponentially rather than linearly. Understanding these impossible distances forces a profound shift in perspective about humanity's place in the cosmos. We are not inhabitants of a universe waiting to be explored. We are prisoners in a cosmic cell defined by the Milky Way galaxy. The bars of our prison aren't made of metal or energy barriers. They're made of space itself. distances so vast they transcend the possibility of crossing them. This distance barrier represents the first and most fundamental reason why intergalactic travel is impossible. Before we even consider energy requirements, time dilation, technological challenges, or any other obstacles, the basic scale of intergalactic space creates barriers that cannot be overcome by any conceivable means. The universe has designed itself at a scale that ensures every galaxy remains an island of permanent isolation in an infinite cosmic archipelago. Chapter 2. Expanding Void. The second crushing barrier to intergalactic travel isn't just the distances themselves, but the fact that space between galaxies is actively expanding, creating new distance faster than any spacecraft could travel. This is an empty void waiting patiently to be crossed. It's a dynamic, growing medium that actively works against any attempt to traverse it. Understanding cosmic expansion reveals why intergalactic travel becomes impossible, not just in practice, but in principle. Most people imagine space as a static container where objects move around like ships on an ocean. But Einstein's general relativity revealed something far stranger. Space itself is a dynamic entity that can stretch, compress, and grow. The expansion of the universe isn't objects flying apart through static space. It is space itself manufacturing new distance at every point, carrying objects along as it grows larger. Dr. Alan Guth, who developed the theory of cosmic inflation, describes space expansion using the analogy of a balloon being inflated. Imagine two ants on the surface of a balloon. As you inflate the balloon, the ants move apart, not because they're walking away from each other, but because the surface itself is expanding beneath them. The space between them literally increases as new surface area is created. This is exactly what happens with galaxies. They re-carried apart by the creation of new space between them. The rate of this expansion was precisely measured by the Planck satellite mission in 2013. Space expands at approximately 70 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, space grows by 70 kilometers every second. This number, called the Hubble constant, determines how rapidly the universe is stretching at every scale. At the distance to Andromeda, 2.5 million light-years, space is expanding at about 54 kilometers per second. That means the void between us and our nearest galactic neighbor grows larger by 54 kilometers every single second, or about 120,000 miles per hour. Even if we launched a spacecraft traveling at 10% the speed of light, an impossibly fast velocity by current standards, the expansion of space would make the journey longer every moment we traveled. This creates what physicists call the cosmological redshift problem for intergalactic travel. As space expands during a journey, the wavelength of any signal or trajectory gets stretched along with the expanding spacetime. A spacecraft aimed at Andromeda today would find its destination increasingly distant as it traveled, like trying to hit a target that moves away faster the closer you get to it. But the expansion problem becomes far worse when we consider the acceleration of cosmic expansion. In 1998, observations of distant supernova revealed that the universe's expansion rate is increasing. Space is stretching faster and faster over time. This acceleration is driven by dark energy, a mysterious force that comprises 68% of the universe's total energy content and acts as a kind of anti-gravity that pushes space apart. Dr. Adam Rees, who shared the Nobel Prize for discovering accelerating expansion, calculated that dark energy is currently causing space to expand at an accelerating rate of about 7 kilometers per second per megaparsec per billion years. This means the Hubble constant itself is growing larger, making space expansion faster and faster as time progresses. This acceleration creates what cosmologists call runaway expansion. Galaxies beyond our local group are moving away from us at velocities that increase exponentially over time. What starts as recession velocities of hundreds of kilometers per second will eventually become thousands, then tens of thousands, then approach the speed of light itself. Objects are disappearing beyond our cosmic horizon as they're carried away by accelerating space. The mathematics of accelerating expansion reveals something truly disturbing about cosmic connectivity. There exists a critical distance called the Hubble distance, currently about 14 billion light-years, beyond which objects recede faster than the speed of light due to space expansion alone. This creates what physicists call the particle horizon, an absolute boundary beyond which no communication or travel is possible, ever. Dr. Lawrence Krauss's calculations show that this particle horizon is shrinking over time due to accelerating expansion. Galaxies that we can observe today will eventually disappear beyond this horizon as they are carried away by space expansion. Future observers will inherit a universe that appears increasingly empty, with fewer and fewer visible galaxies as cosmic expansion erases evidence of the broader cosmos. For galaxies within our local group, the situation appears better because these objects are gravitationally bound together and won't be carried apart by expansion. However, even here the expansion of space creates travel problems. The space between local group galaxies is still expanding, even though the galaxies themselves aren't being carried apart. This means that journeys between local group members must fight against the expansion of the intervening space. Imagine trying to swim across a river where the water level rises faster than you can swim. Even if the shores aren't moving apart, the growing volume of water between them makes the crossing increasingly difficult. Similarly, the expanding space between local group galaxies creates an energy barrier that grows larger during any attempted journey. Recent computer simulations by Dr. Avi Loeb's team have modeled the effects of cosmic expansion on hypothetical intergalactic journeys. Their results show that even within the local group, space expansion adds significant energy costs to any trip. A spacecraft must continuously accelerate not just to reach its destination, but to compensate for the new space being created during the journey. The longer the trip takes, the more expansion works against the traveler. This expansion barrier becomes absolute for any journey that takes longer than the cosmic crossing time, the time required for space expansion to double the distance to your destination. For most intergalactic distances, this crossing time is shorter than any realistic travel time, meaning space expansion makes the destination literally unreachable regardless of spacecraft velocity. The psychological implications of expanding space are profound. We exist in a universe that is actively working to isolate every galaxy from every other galaxy. Space itself conspires against cosmic connection, manufacturing distance faster than intelligence can overcome it. This isn't a temporary condition that might improve with better technology. It is a fundamental feature of cosmic geometry that grows stronger over time. The expansion also creates temporal paradoxes for intergalactic travel. Due to space expansion, the present moment is different at different cosmic locations. When we observe Andromeda, we see it as it existed 2.5 million years ago. But due to relativistic effects and cosmic expansion, there's no absolute way to define what's happening now in Andromeda. Any spacecraft journey must navigate not just through expanding space, but through the relativistic complexities of cosmic time. Dr. Sean Carroll's work on the arrow of time reveals that cosmic expansion is intimately connected to the flow of time itself. The expansion of space is driven by the increase of entropy, the same fundamental force that makes time flow forward rather than backward. This means that fighting against cosmic expansion is equivalent to fighting against time itself. Space expansion represents entropy increase on a cosmic scale, making it as impossible to reverse as making a broken egg reassemble itself. The accelerating expansion driven by dark energy makes this barrier increasingly impermeable. Current observations suggest that dark energy density remains constant as space expands, meaning that the total amount of dark energy in the universe increases as new space is created. This creates a positive feedback loop where expansion creates more dark energy, which drives faster expansion, which creates even more dark energy. Some cosmological models predict that this accelerating expansion will eventually lead to a big rip scenario where space expands so rapidly that it overcomes all other forces, tearing apart galaxies, stars, planets, and eventually even atoms themselves. Long before this cosmic catastrophe, accelerating expansion will have made intergalactic travel completely impossible by carrying all distant galaxies beyond the cosmic horizon. Understanding expanding space reveals that intergalactic travel isn't just difficult. It is fighting against the fundamental direction of cosmic evolution. The universe is designed to become increasingly sparse, increasingly isolated, increasingly empty as time progresses. Every galaxy is destined to become an island in an ever-growing ocean of empty space. This expansion barrier operates independently of any technological limitations. Even with perfect propulsion systems, unlimited energy, and flawless navigation, travelers must still contend with the basic fact that their destination is moving away from them due to forces beyond anyone's control. Space expansion represents a cosmic law that no intelligence, no matter how advanced, can circumvent or overcome. The expanding void between galaxies isn't just an obstacle to travel. It is proof that the universe operates by rules designed to preserve cosmic mystery rather than enable cosmic conquest. Each galaxy exists as a preserve of complexity and consciousness, surrounded by growing barriers of empty space that ensure permanent isolation from all other galactic preserves. Chapter 3. Energy Prison. Even if we could somehow overcome the problems of distance and expansion, the energy requirements for intergalactic travel create barriers so absolute they mock every energy source available in our solar system. The physics of acceleration, the need to carry fuel, and the basic relationships between mass and energy conspire to create what physicists call the tyranny of the rocket equation, mathematical laws that make intergalactic travel energetically impossible regardless of technological advancement. To understand why energy creates an insurmountable prison, let's start with the most optimistic scenario imaginable. Suppose we want to send a small probe, just 1 kilogram of mass, to Andromeda at a mere 10% of light speed. This would reduce the journey time to a brief 25 million years and would require overcoming relatively modest relativistic effects. The energy calculation for this seemingly reasonable goal reveals the absolute impossibility of the enterprise. Dr. Robert Forward, the physicist who spent decades studying interstellar propulsion, calculated the energy requirements for relativistic travel. To accelerate 1 kilogram to 10% of light speed requires approximately 4.5 times 1014 joules of kinetic energy. That's 450 trillion joules, roughly equivalent to the total annual energy consumption of the United States. For a 1 kilogram probe to travel at 10% of light speed. And this calculation ignores the energy needed to carry fuel, the energy lost to inefficiency, and the energy required for deceleration at the destination. The energy requirement scales catastrophically with desired velocity. Reaching 50% of light speed requires not just 5 times more energy, but more than 15 times more energy due to relativistic effects. At 90% of light speed, the energy requirement becomes more than 100 times larger than the non-relativistic calculation would predict. The mathematics of special relativity creates an exponential energy barrier that approaches infinity as velocity approaches the speed of light. But the fuel problem makes these already impossible numbers even worse. Unlike a car that can refill at gas stations, a spacecraft must carry all its fuel from the beginning of the journey. This creates what rocket engineers call the tyranny of the rocket equation, the exponential relationship between fuel mass and achievable velocity. To go twice as fast, you need exponentially more fuel. To carry more fuel, you need more fuel to accelerate the extra fuel mass. Dr. Konstantin Tsiolkovsky derived the fundamental rocket equation in 1903, showing that the final velocity of a rocket depends exponentially on the ratio of initial mass to final mass. For chemical rockets, achieving escape velocity from Earth requires a fuel-to-payload ratio of about 20:1. Reaching interplanetary velocities requires ratios of hundreds to 1. For relativistic velocities needed for intergalactic travel, the fuel-to-payload ratios become literally astronomical. Consider the math for our 1 kilogram probe traveling at 10% light speed using the most efficient possible chemical propulsion. The fuel-to-payload ratio would exceed 1040:1. That means carrying 1,040 kilograms of fuel, a mass greater than that of the entire observable universe, to accelerate 1 kilogram to 10% of light speed. The fuel requirements exceed the total amount of matter that exists. Even with perfect matter-antimatter annihilation, the most efficient energy conversion possible, according to physics, the numbers remain impossibly large. Matter-antimatter reactions convert mass to energy with 100% efficiency, compared to chemical reactions that convert less than 0.0000001% of mass to energy. Yet even with this perfect efficiency, achieving relativistic velocities requires fuel masses that dwarf available resources. Dr. Giovanni Volpetti's calculations for antimatter-powered spacecraft show that reaching 10% of light speed requires a fuel-to-payload ratio of approximately 1,000:1, even with perfect matter-antimatter propulsion. For our 1 kilogram probe, this means 1,000 kilograms of antimatter fuel. Producing 1 gram of antimatter using current methods would require more energy than the entire United States generates in a year. Producing 1,000 kilograms would require more energy than our sun produces in thousands of years. The antimatter production problem represents another absolute barrier. Antimatter doesn't exist naturally in significant quantities in our universe. It must be created artificially using particle accelerators, and current methods are staggeringly inefficient. CERN's antimatter factory can produce about 10 nanograms of antiprotons per year while consuming billions of watts of electricity. At current production rates, manufacturing 1 gram of antimatter would take millions of years. Even if we solve the production problem, storing antimatter presents additional impossibilities. Antimatter annihilates instantly upon contact with ordinary matter, releasing tremendous energy. Containing antimatter requires magnetic or electric field systems that themselves consume enormous amounts of energy. Current antimatter storage systems can contain only a few atoms at a time for brief periods. Storing kilograms of antimatter for interstellar journeys would require energy storage and containment systems that exceed any conceivable technology. The energy barrier becomes even more insurmountable when we consider realistic spacecraft requirements. Our 1 kilogram probe represents just the scientific instruments, not the spacecraft structure, life support systems, navigation equipment, communication systems, or radiation shielding required for actual missions. A realistic intergalactic spacecraft would mass thousands or millions of kilograms, multiplying the already impossible energy requirements by factors that destroy any hope of feasibility. Dr. Mark Millis, who directed NASA's Breakthrough Propulsion Physics project, calculated energy requirements for realistic interstellar missions. His analysis showed that sending a modest scientific mission to the nearest star would require energy equivalent to the entire United States' annual electricity production. Scaling these calculations to intergalactic distances yields energy requirements that exceed the total energy output of our Sun over millions of years. Alternative propulsion concepts like fusion rockets, ion drives, and solar sails failed to solve the fundamental energy problem. Fusion rockets could theoretically achieve higher specific impulse than chemical rockets, but fusion energy represents only 0.7% mass-to-energy conversion compared to antimatter's 100%. The fuel mass requirements remain impossibly large. Ion drives achieve very high efficiency, but produce extremely low thrust, requiring decades to accelerate spacecraft to even modest velocities. Solar sails eliminate the need to carry fuel by using radiation pressure from stars for propulsion. However, solar radiation pressure decreases as the inverse square of distance from the star. Beyond the outer solar system, solar radiation becomes too weak to provide meaningful acceleration. Between galaxies, where stellar radiation is negligible, solar sails become completely useless. Even theoretical breakthrough propulsion concepts like fusion ramjets encounter insurmountable energy barriers for intergalactic travel. Fusion ramjets would collect interstellar hydrogen as fuel during flight, eliminating the need to carry fuel mass. However, the density of interstellar medium is approximately 1 atom per cubic centimeter. At intergalactic distances, where the density drops to perhaps 1 atom per cubic meter, ramjet propulsion becomes impossible. The energy barriers extend beyond propulsion to every aspect of intergalactic travel. Maintaining spacecraft systems for million-year journeys requires energy for life support, computers, communication, navigation, and repairs. Protecting crews or equipment from cosmic radiation requires massive shielding that adds weight and energy requirements. Communicating with Earth across intergalactic distances requires transmitter power levels that dwarf current capabilities. Recent studies of interstellar dust and radiation environments reveal additional energy costs for intergalactic travel. At relativistic velocities, even tiny dust grains become devastating projectiles that can destroy spacecraft. Protection against these impacts requires either massive physical shielding or energy-intensive deflector systems. The energy cost of protection systems often exceeds the energy available for propulsion. Dr. James Benford's analysis of spacecraft vulnerability to interstellar environments shows that realistic protection systems would increase spacecraft mass by factors of 10 to 100, correspondingly increasing fuel requirements. The energy needed for protection against the space environment between galaxies would be orders of magnitude larger than protection requirements for interstellar travel within our galaxy. The energy prison that confines us to our galaxy isn't a temporary technological limitation waiting for clever engineering solutions. It's a fundamental consequence of the relationship between mass, energy, and velocity described by Einstein's equations. These relationships are as absolute and unchangeable as the laws of thermodynamics. No future technology can violate conservation of energy or eliminate the exponential increase in energy requirements for relativistic travel. Understanding the energy prison reveals why serious physicists describe intergalactic travel as impossible rather than merely difficult. The energy requirements exceed not just current capabilities, but the total energy resources available in our solar system. Even harnessing the entire energy output of our sun for millions of years wouldn't provide sufficient energy for intergalactic missions, carrying meaningful payloads at reasonable velocities. This energy barrier operates independently of all other obstacles to intergalactic travel. Even if we could solve problems of distance, time, navigation, and human survival, the basic energy requirements would still make intergalactic travel absolutely impossible with any conceivable technology based on known physics. Chapter 4. Time Trap. Perhaps the cruelest barrier to intergalactic travel isn't the distance or energy, it's time itself. Einstein's theory of relativity reveals that time flows differently for travelers approaching light speed, creating paradoxes that make intergalactic journeys meaningless even if all other obstacles were overcome. The mathematics of time dilation the relationship between space and time, and the finite nature of human consciousness create temporal traps that transform intergalactic travel from a journey to nowhere into a journey to no one. The fundamental problem lies in Einstein's discovery that time is not absolute but relative to the observer as velocity. As spacecraft approach light speed, time aboard the ship slows down relative to time experienced by those remaining behind. This isn't a technological effect that can be eliminated with better engineering. It is a fundamental property of spacetime itself, as unchangeable as the fact that 2 + 2 = 4. Dr. Brian Greene explains time dilation using the concept of spacetime intervals. All objects move through spacetime at a constant velocity, the speed of light. When an object is stationary in space, all its motion occurs through time. When an object moves rapidly through space, less of its motion occurs through time. The faster you travel through space, the slower you travel through time. At light speed, all motion occurs through space and none through time, meaning time stops entirely for objects traveling at light speed. For a journey to Andromeda at 90% of light speed, the time dilation factor is approximately 2.3. This means that while 2.8 million years pass on Earth, travelers experience only 1.2 million years during the journey. From the traveler's perspective, the journey takes only 1.2 million years. From Earth's perspective, they've been gone for 2.8 million years. Both measurements are equally valid according to relativity. There is no absolute time that determines which is correct. But these numbers reveal the cruel joke that relativity plays on intergalactic travelers. Even with extreme time dilation, the journey still requires more than 1 million years from the traveler's perspective. No human civilization has ever existed for such periods. No species remains biologically unchanged across such timescales. No language, culture, government, or social institution survives million-year periods. The concept of returning home becomes meaningless when home has evolved beyond recognition during your absence. The temporal barriers become even more severe when we consider round-trip journeys. A round trip to Andromeda at 90% light speed would take 2.4 million years from the traveler's perspective and 5.6 million years as measured on Earth. The Earth that travelers left would be as different from their return Earth as modern humans are from our early ancestors who first learned to use fire. Every person, every institution, every aspect of the civilization that sent them would be gone, replaced by societies and cultures evolved beyond recognition. Dr. Carl Sagan often illustrated these time effects by pointing out that the entire recorded history of human civilization spans only about 5,000 years. A single intergalactic journey would last hundreds of times longer than all of human history combined. The temporal scale makes the journey not just impractical, but literally incomprehensible to human consciousness, which is adapted to think in terms of decades, not millennia. The psychological impact of these timescales goes beyond mere duration. Human consciousness, human relationships, and human meaning are all tied to shared temporal experience. Love, friendship, family bonds, and social connections require synchronous existence. They cannot survive when participants experience time at radically different rates. Intergalactic travelers would find themselves temporally isolated not just from their home planet, but from the fundamental human experience of shared time. Recent studies in psychology and neuroscience reveal that human consciousness is intimately tied to temporal continuity. Our sense of self, our memories, and our ability to form meaningful relationships all depend on experiencing time at rates compatible with other humans. The extreme time dilation of intergalactic travel would create forms of temporal isolation that could destroy the psychological foundations of human consciousness. But the time problem goes deeper than individual psychology. The very concept of purpose becomes meaningless across million-year timescales. Any scientific mission, exploration goal, or human objective that motivates intergalactic travel would be obsolete long before travelers reach their destination. The questions that seemed important at departure would be forgotten history by arrival. The civilizations that sent the mission would have evolved new interests, new technologies, new scientific paradigms completely unrelated to the original mission goals. Dr. Freeman Dyson's calculations of technological change rates suggest that human technology advances by factors of thousands to millions over century-long timescales. Extrapolating these rates across million-year periods yields technological changes so vast they're impossible to conceptualize. The civilization that receives returning intergalactic travelers would possess technology as far beyond current capabilities as our smartphones are beyond stone tools. This technological evolution creates what physicists call the temporal relevance problem. Any information, samples, or discoveries returned by intergalactic travelers would be obsolete compared to what their home civilization had learned during the millions of years of their absence. The journey becomes scientifically meaningless because home civilizations advance far beyond the mission objectives during the travel time. The time trap extends to communication between intergalactic travelers and their home worlds. Radio signals travel at light speed, so communication with a spacecraft near Andromeda involves 2.5 million-year delays each way. A simple conversation becomes a 5 million-year exchange. By the time travelers receive responses to their messages, the civilizations that sent the responses will evolve beyond recognition. This communication delay creates what Dr. John Pierce called the isolation paradox. Intergalactic travelers become completely cut off from their origins, unable to receive guidance, updates, or even confirmation that their home civilization still exists. They journey into the cosmic equivalent of sensory deprivation, isolated not just spatially, but temporally from any meaningful connection to their origins. The mathematics of relativity creates additional temporal paradoxes that make round-trip intergalactic travel logically problematic. Due to the relativity of simultaneity, events that are simultaneous in one reference frame occur at different times in other reference frames. Travelers departing for Andromeda and Earthbound observers disagree about the sequence and timing of events throughout the journey, making it impossible to maintain consistent temporal relationships. These relativistic effects mean that intergalactic travelers exist in a different temporal reference frame from their origins. They don't just travel to a distant place. They travel to a different temporal relationship with the universe. The very concepts of departure and arrival become ambiguous when travelers and their origins experience time flow at different rates. Dr. Kip Thorne's work on relativistic astrophysics reveals that extreme time dilation effects create temporal shear in social and biological systems. Groups of intergalactic travelers would experience different time dilation effects, depending on their exact velocities and trajectories, causing them to age at different rates relative to each other. A crew that departs together could arrive at their destination having experienced different amounts of personal time, destroying any sense of shared experience. The time trap becomes absolute when we consider that intergalactic distances require either million-year journey times or velocities so close to light speed that time dilation approaches infinity. At 99.9999% of light speed, time dilation becomes so extreme that travelers experience almost no personal time during the journey. But such velocities require infinite energy according to relativity. The closer you approach the speed of light, the more energy you need, but also the less personal time you experience. This creates what cosmologists call the temporal paradox of relativistic travel. To minimize personal time during intergalactic journeys, you must travel at velocities that require impossible energy levels. To travel at achievable velocities, he must accept journey times that exceed the duration of civilizations, species, and possibly intelligent life itself. Understanding the time trap reveals that intergalactic travel isn't just physically impossible, it's temporally meaningless. Even if we could solve every other obstacle, the time required for intergalactic journeys transcends every timescale relevant to human consciousness, human civilization, and human existence. The journey times are so vast they exist beyond the scope of any human purpose or meaning. The temporal barriers to intergalactic travel aren't waiting for future technology to overcome them. They're fundamental properties of spacetime itself, as absolute and unchangeable as the geometry of triangles. Time dilation is not a bug in the design of the universe. It is a feature that ensures every intelligent species remains temporally isolated within its cosmic era, unable to transcend the flow of time that defines its existence. The time trap represents perhaps the most philosophical barrier to intergalactic travel, forcing us to confront the relationship between consciousness and temporal experience. We are not just imprisoned by distance and energy. We are imprisoned by time itself, confined to experience reality within temporal boundaries that make cosmic exploration fundamentally impossible. Chapter 5. Speed Limits. The ultimate barrier to intergalactic travel lies in the cosmic speed limit itself. The speed of light in vacuum, approximately 300,000 kilometers per second. This isn't merely the fastest speed we know how to achieve. It's the maximum possible velocity for anything with mass according to the fundamental structure of spacetime. Understanding why this speed limit exists and why it cannot be overcome reveals that it's the deepest reason why intergalactic travel is absolutely impossible. Einstein's special relativity demonstrates that the speed of light isn't just another velocity like sound speed or escape velocity. It has a fundamental property of spacetime geometry itself. The speed of light represents the rate at which causality propagates through the universe, the maximum speed at which cause can influence effect. This speed limit is woven into the fabric of reality so fundamentally that violating it would be equivalent to violating logic itself. Dr. Albert Einstein showed that mass and energy are related through his famous equation E=mc. But the complete equation, less well known, is E=pc² plus mech²², where p represents momentum. This equation reveals that as an object's velocity approaches the speed of light, its relativistic mass approaches infinity. Accelerating any massive object to light speed would require infinite energy, an amount that doesn't exist in the universe. The mathematics becomes clear when we examine the Lorentz factor. Gamma equals 1√1v² per c², which describes how relativistic effects scale with velocity. At everyday velocities, this factor is essentially 1, meaning relativistic effects are negligible. But as velocity approaches the speed of light, the denominator approaches 0, causing the Lorentz factor to approach infinity. This means time dilation, length contraction, and energy requirements all become infinite as velocity approaches light speed. For intergalactic travel, this speed limit creates an insurmountable barrier because even light speed isn't fast enough. Light takes 2.5 million years to travel from our galaxy to Andromeda. Even if we could somehow achieve light speed, which requires infinite energy, the journey would still take millions of years. And since massive objects cannot reach light speed under any circumstances, real spacecraft must travel slower, making journey times even longer. Dr. John Wheeler illustrated the absoluteness of the light speed barrier using thought experiments about the structure of spacetime. He showed that exceeding light speed would allow effects to precede their causes, creating logical paradoxes that would destroy the rational structure of reality. Faster than light travel would enable time travel to the past, creating scenarios where travelers could prevent their own departure. Logical contradictions that suggest the universe is designed to prevent such violations. But the speed limit barrier goes deeper than just the prohibition on faster-than-light travel. Even achieving substantial fractions of light speed requires exponentially increasing amounts of energy. Reaching 90% of light speed requires more than twice as much energy as non-relativistic calculations would predict. Reaching 99% requires more than 7 times as much energy. The closer you approach the speed limit, the more impossible the energy requirements become. Recent experimental verification of these relativistic effects comes from particle accelerators like the Large Hadron Collider, where subatomic particles are accelerated to 99.9999% of light speed. These experiments confirm that the energy required to accelerate particles increases exponentially as velocity approaches light speed, exactly as Einstein predicted. No amount of energy can push particles that final fraction of a percent to reach actual light speed. The speed limit problem becomes even more constraining when we consider the practical velocities achievable with realistic propulsion systems. Chemical rockets can achieve perhaps 0.001% of light speed. Nuclear rockets might reach 0.01% of light speed. Even theoretical fusion rockets would be limited to perhaps 0.1% of light speed. At these realistic velocities, intergalactic journey times stretch to hundreds of millions of years. Dr. Robert Bussard proposed interstellar ramjets that would collect hydrogen fuel from the interstellar medium during flight, theoretically allowing acceleration to substantial fractions of light speed. However, calculations by Dr. John Ford showed that drag effects from collecting interstellar hydrogen actually limit ramjet velocity to about 12% of light speed. Even with this theoretical maximum, journeys to Andromeda would require more than 20 million years. The speed limit also creates navigation and collision problems that make high-velocity intergalactic travel incredibly dangerous. At substantial fractions of light speed, even tiny dust grains become devastating projectiles carrying enormous kinetic energy. A single hydrogen atom striking a spacecraft at 50% of light speed carries as much energy as a rifle bullet. Dust grains become nuclear weapons. Navigation errors that might be minor inconveniences at low velocities become catastrophic disasters at relativistic speeds. Dr. Eugene Mao calculated that spacecraft traveling at 10% of light speed would encounter approximately 1,000 dust grain impacts per square meter per second. Each impact would release energy equivalent to small explosions, gradually eroding any spacecraft structure. Protection against these impacts requires massive shielding that adds weight and reduces achievable velocity, creating a design paradox where faster travel requires heavier protection that prevents faster travel. The fundamental speed limit also affects communication and navigation systems essential for intergalactic travel. Radio signals travel at light speed, meaning communication with spacecraft traveling at substantial fractions of light speed involves extreme Doppler shifts that distort signal frequencies. Navigation systems that depend on receiving signals from Earth or from positioning satellites become increasingly unreliable as spacecraft velocity approaches the speed limit. Recent theoretical work on Alcubierre drives and other speculative faster-than-light propulsion concepts reveals that these supposed solutions to the speed limit problem actually make the situation worse. The Alcubierre drive would theoretically allow faster-than-light travel by contracting space in front of a spacecraft and expanding space behind it. However, calculations show that such a device would require exotic matter with negative energy density, a form of matter that probably doesn't exist and definitely cannot be manufactured. Dr. Chris van den Broek's improved version of the Alcubierre drive would require only a few solar masses worth of exotic matter with negative energy density. But even if such matter existed, the energy requirements for creating and manipulating it would exceed the total energy available in our solar system. The proposed solutions to the speed limit problem require resources and technologies that are even more impossible than achieving light speed through conventional acceleration. Wormhole travel, theoretically allowing instantaneous transportation across cosmic distances, faces similar impossibilities. Wormholes, if they exist, would require enormous amounts of exotic matter to keep them stable and traversable. The energy requirements for creating artificial wormholes suitable for spacecraft passage would dwarf the energy needed for conventional interstellar travel. Moreover, most theoretical models suggest that wormholes would be extremely unstable, collapsing before any spacecraft could traverse them. The speed limit barrier extends beyond propulsion to every aspect of spacecraft design and operation. Life support systems operating for million-year journeys must function reliably across timescales that exceed the operational lifetime of any technology humans have ever built. Computer systems must maintain functionality and data integrity across geological timescales. Material structures must resist cosmic radiation, thermal cycling, and mechanical stress for periods longer than human civilization has existed. Dr. Robert Forward's studies of interstellar spacecraft design reveal that the speed limit creates cascading constraints that make spacecraft engineering increasingly difficult. As desired velocity increases, faster spacecraft require lighter construction to minimize fuel requirements, but they also require stronger construction to survive relativistic impacts and structural stresses. These conflicting requirements create engineering contradictions that become impossible to resolve at high velocities. The psychological effects of the speed limit on crew members during intergalactic journeys would be devastating. Traveling for millions of years at substantial fractions of light speed means complete isolation from human civilization, with no possibility of communication or rescue. The knowledge that you're traveling as fast as physics allows, yet still requiring geological timescales to reach your destination, would create forms of existential despair that no human psychology could endure. Understanding the cosmic speed limit reveals that intergalactic travel isn't just prohibited by engineering limitations or energy constraints. It is prohibited by the fundamental structure of reality itself. The speed of light isn't just a barrier that might be overcome with better technology. It's an absolute boundary built into the mathematical foundations of spacetime. This speed limit represents the universe's ultimate law against cosmic travel, ensuring that every galaxy remains permanently isolated from every other galaxy. No intelligence, regardless of technological advancement, can overcome this barrier, because doing so would require violating the logical structure of reality itself. The cosmos has designed itself with speed limits that guarantee eternal isolation between its galactic islands of complexity and consciousness. Chapter 6. Fuel impossibility beyond the energy calculations lies an even more crushing reality. There simply isn't enough fuel in our entire solar system to power intergalactic travel. The mass of propellant required exceeds the total mass of planets, moons, asteroids, and comets combined. Even converting every atom of matter within reach into perfectly efficient fuel wouldn't provide enough energy for realistic intergalactic missions. This fuel barrier transforms intergalactic travel from merely impossible to absurdly impossible. To understand the scope of the fuel problem, let us examine the most optimistic scenario. A tiny 1 kilogram probe traveling to Andromeda using perfect matter-antimatter annihilation for propulsion. Antimatter represents the theoretical maximum efficiency for chemical energy. Complete conversion of mass to energy according to Einstein SE equals mc. If we can't make intergalactic travel work with perfect antimatter fuel, it can't work with any fuel. Dr. Robert Forward's calculations for antimatter-propelled spacecraft show that even with perfect efficiency, accelerating 1 kilogram to 10% of light speed requires approximately 1,000 kilograms of antimatter fuel. This fuel-to-payload ratio of 1,000 to 1 assumes perfect conversion efficiency, perfect spacecraft design, and no energy losses, assumptions that are themselves impossible to achieve in practice. The antimatter production problem immediately reveals the impossibility. Currently, CERN's antimatter factory produces about 10 nanograms of antiprotons per year, while consuming enormous amounts of electricity. To produce 1 gram of antimatter would require millions of years at current production rates. To produce the 1,000 kilograms needed for our hypothetical probe would require billions of years, longer than the current age of the universe. But the production timeline is only part of the problem. The energy cost of antimatter production using current methods exceeds the energy content of the antimatter by factors of billions to trillions. Creating 1 joule of antimatter energy requires consuming thousands of billions of joules of electricity. The energy investment needed to produce intergalactic fuel exceeds the energy output of that fuel by ratios so large they transcend practicality. Even if we achieve perfect 100% efficiency in antimatter production, a thermodynamic impossibility, we would still need to convert enormous amounts of ordinary matter into antimatter. The 1,000 kilograms of antimatter fuel for our 1 kilogram probe would require converting 2,000 kilograms of ordinary matter. Half becomes matter, half becomes antimatter. But the energy required to perform this conversion would itself require additional fuel, creating an infinite regression that makes the problem unsolvable. Dr. Giovanni Volpetti's more detailed analysis includes the energy costs of antimatter storage and handling systems. Antimatter must be stored in perfect vacuum using magnetic or electric field containment systems that prevent any contact with ordinary matter. These containment systems require continuous energy input to maintain the fields, and they must be absolutely perfect. Any containment failure would result in explosive annihilation of the entire fuel supply. The containment energy requirements scale catastrophically with the amount of antimatter being stored. Current antimatter storage systems can contain only a few atoms for brief periods while consuming enormous amounts of power. Scaling these systems to contain kilograms of antimatter for years or decades would require energy storage and power generation systems that exceed the mass and complexity of the spacecraft they were supposed to fuel. Realistic spacecraft requirements make the fuel problem exponentially worse. Our 1 kilogram probe represents only the scientific payload, not the spacecraft structure, propulsion system, power generation, life support, navigation, communication, or radiation shielding required for actual missions. A minimally functional intergalactic spacecraft would mass thousands of kilograms, requiring millions of kilograms of antimatter fuel. The fuel requirements for crewed intergalactic missions transcend any reasonable concept of possibility. Dr. Gerald O'Neill, Space Habitat Studies suggest that self-sufficient human communities require approximately 1,000 tons of material per person for life support, manufacturing, agriculture, and social infrastructure. An intergalactic colony ship carrying even 100 people would mass at least 100,000 tons, requiring 100 million tons of antimatter fuel. To put this in perspective, 100 million tons of antimatter represents more antimatter than could be produced by converting the entire mass of Earth's moon using perfect conversion efficiency. The fuel requirements for crewed intergalactic travel exceed the mass of planetary bodies. We would need to dismantle entire worlds to generate enough fuel for single missions. Alternative fuel sources fail to solve the fundamental problem. Nuclear fusion, often proposed for interstellar travel, converts only 0.7% of mass to energy compared to antimatter's 100% efficiency. Fusion-powered intergalactic missions would require fuel masses 100 times larger than antimatter missions. Instead of needing moon mass amounts of fuel, fusion missions would require asteroid belt mass amounts of fuel. Chemical propulsion makes the problem so much worse it enters the realm of comedy. Chemical rockets convert perhaps 0.0001% of fuel mass to kinetic energy. Intergalactic missions using chemical propulsion would require fuel masses comparable to the mass of the Sun itself. The concept becomes so absurd, it loses any connection to physical reality. Even theoretical, external energy sources like laser propulsion or solar sails face insurmountable fuel-equivalent problems. Laser propulsion systems require enormous ground-based power stations to generate the laser beams that accelerate spacecraft. Dr. Philip Lubin's calculations for laser-propelled interstellar missions show that achieving meaningful acceleration requires laser power levels measured in terawatts, equivalent to the total energy generation capacity of human civilization. Scaling laser propulsion to intergalactic distances would require laser systems more powerful than the total energy output of our Sun. Building such systems would require industrial capabilities that exceed anything achievable with solar system resources. The fuel for laser propulsion becomes stellar-level energy generation capacity that no conceivable civilization could construct. Solar sails avoid carrying fuel mass by using radiation pressure for propulsion, but they suffer from inverse square law problems that make them useless for intergalactic travel. Solar radiation pressure becomes negligible beyond the outer solar system, and it becomes essentially zero in the void between galaxies, where there are no nearby stars to provide radiation pressure. The fuel storage problem extends beyond propellant mass to include fuel degradation over journey timescales measured in millions of years. No fuel remains stable across geological timescales. Chemical fuels decompose, nuclear fuels undergo radioactive decay, and even antimatter storage systems would suffer equipment failures over million-year periods. Intergalactic missions would need to carry not just enormous amounts of fuel, but also industrial systems capable of fuel production and processing during the journey. Dr. Eugene Maloff's studies of long-duration spacecraft systems reveal that fuel systems, reliable enough for intergalactic travel, would themselves mass more than the spacecraft they redesigned to power. Backup systems, redundancy, spare parts, and fuel processing equipment would multiply spacecraft mass by factors that make fuel requirements even more impossible. The waste heat problem from fuel processing and propulsion systems creates additional impossibilities. Antimatter annihilation produces enormous amounts of heat that must be radiated away to prevent spacecraft destruction. The radiator systems required to handle waste heat from intergalactic propulsion would be massive structures requiring additional structural mass and fuel to accelerate. Recent studies of spacecraft thermal management show that efficient heat radiation requires radiator areas measured in square kilometers for high-power systems. Intergalactic spacecraft would need radiator systems larger than cities, with structural masses that multiply fuel requirements by additional factors of thousands. The fuel problem also includes the energy costs of fuel refinement and processing during multi-million-year journeys. Raw materials must be converted to usable fuel through industrial processes that require energy, equipment, and skilled operators. The industrial infrastructure required for fuel processing during intergalactic journeys would itself require enormous amounts of fuel to transport and operate. Understanding the fuel impossibility reveals that intergalactic travel fails not just at the level of energy calculations, but at the level of basic resource availability. There isn't enough matter in our solar system to fuel intergalactic missions using any conceivable technology. Even with perfect efficiency, unlimited time for fuel production, and theoretical perfect propulsion systems, the fuel requirements exceed available resources by factors of millions to billions. This fuel barrier operates independently of all other obstacles to intergalactic travel. Even if we could solve problems of time, navigation, human survival, and spacecraft engineering, the basic requirement for fuel would still make intergalactic travel absolutely impossible. The universe has designed itself so that the fuel requirements for cosmic travel exceed the resources available to any conceivable civilization. The fuel impossibility represents perhaps the most concrete and undeniable barrier to intergalactic travel, forcing us to confront the fact that our cosmic ambitions are limited not just by physics and engineering, but by the basic arithmetic of resource availability in a finite universe. Chapter 7. Navigation Nightmare. Even if we somehow solved the impossible problems of distance, energy, and fuel, the challenge of navigating across intergalactic space creates obstacles that no conceivable technology can overcome. The universe actively conspires against intergalactic navigation through cosmic expansion, stellar motion, gravitational perturbations, and the basic problem of finding targets that move and change across million-year timescales. Understanding these navigation barriers reveals another layer of fundamental impossibility in intergalactic travel. The first navigation nightmare comes from the fact that galaxies are not stationary targets waiting patiently to be reached. Every galaxy in the universe is moving through space with complex motions that change over time. Our own Milky Way galaxy is rotating, with our solar system orbiting the galactic center at approximately 220 kilometers per second. Andromeda has its own rotation and orbital motions. The local group of galaxies is falling toward the Virgo cluster at 600 kilometers per second. These motions occur on top of cosmic expansion, creating a navigation problem where both starting point and destination are constantly changing. Position. Dr. Vera Rubin's studies of galactic motion revealed that galaxies don't move in simple, predictable ways. Dark matter halos surrounding galaxies create gravitational effects that influence galactic orbits in ways we do not fully understand. The distribution of dark matter changes over time as cosmic structures evolve, making long-term predictions of galactic motion increasingly uncertain. Any navigation system for intergalactic travel must predict where a target galaxy will be millions of years in the future. But our understanding of cosmic dynamics makes such predictions impossible. The cosmic expansion problem makes navigation exponentially more difficult because it changes the geometry of space during the journey. A spacecraft aimed at Andromeda's current position would miss its target, because space expansion carries the destination away from its apparent location. The spacecraft must be aimed at where Andromeda will be millions of years in the future, accounting for its motion through expanding space, a calculation that becomes increasingly uncertain over cosmic timescales. Dr. Sean Carroll's work on cosmic expansion shows that the expansion rate itself changes over time due to the evolving balance between matter, dark energy, and cosmic curvature. Dark energy density appears constant as space expands, but matter density decreases as the universe grows larger. This changing energy balance affects expansion rates in ways that make long-term navigation calculations impossible to perform accurately. The gravitational perturbation problem adds another layer of navigation impossibility. Every massive object in the universe exerts gravitational influence that slightly deflects spacecraft trajectories. Over the million-year timescales required for intergalactic travel, these tiny deflections accumulate into enormous course deviations. The gravitational influence of stars, planets, black holes, dark matter concentrations, and galaxy clusters all combine to create chaotic trajectory variations that no navigation system can predict or correct. Recent studies of spacecraft trajectory prediction show that gravitational perturbations make long-term navigation inherently chaotic. Dr. Jacques Lasker's calculations of planetary motion demonstrate that even within our solar system, orbital predictions become unreliable beyond about 100 million years due to chaotic gravitational interactions. Extending these calculations to intergalactic scales, where gravitational influences are weaker but journey times are thousands of times longer, makes navigation prediction completely impossible. The three-body problem in classical mechanics proves that systems with just three gravitationally interacting objects can exhibit chaotic behavior that makes long-term predictions impossible. Intergalactic navigation involves billions of gravitating objects. Every star, planet, black hole, and dark matter concentration between galaxies. The resulting gravitational chaos makes trajectory prediction impossible beyond relatively short timescales. Communication delays create additional navigation impossibilities for intergalactic travel. Radio signals travel at light speed, so communication with spacecraft approaching Andromeda involves delays of millions of years each way. By the time navigation corrections reach the spacecraft, both the spacecraft and its destination have moved to completely different positions. Real-time course correction becomes physically impossible due to the finite speed of light. Dr. Ronald Bracewell's studies of interstellar communication revealed that meaningful navigation assistance requires communication delays shorter than characteristic motion timescales. For intergalactic distances, communication delays exceed galactic orbital periods, making it impossible to provide useful navigation updates to spacecraft during their journeys. Intergalactic travelers would be completely cut off from navigation assistance for the duration of their missions. The stellar motion problem compounds navigation difficulties because individual stars within galaxies are also moving. Over million-year timescales, stellar motions within galaxies change the internal structure and appearance of target galaxies. The specific destinations within target galaxies, particular star systems, regions, or cosmic phenomena, would have moved to different locations by the time travelers arrive. Dr. Fritz Zwicky's studies of stellar kinematics show that stars in galaxy centers move at velocities of hundreds of kilometers per second. Over million-year journey times, these motions carry stars across distances larger than current solar system dimensions. Any navigation system aimed at specific locations within target galaxies would find those locations completely changed upon arrival. The cosmic reference frame problem creates fundamental conceptual difficulties for intergalactic navigation. In a universe where space itself expands and all objects are in constant motion, there's no absolute reference frame for defining position and velocity. Navigation systems must choose arbitrary reference frames, but different choices lead to different navigation solutions. The lack of absolute cosmic reference frames makes navigation calculations inherently ambiguous. Einstein's general relativity shows that space and time are curved by gravitational fields, making the concept of straight-line travel between galaxies undefined. Spacecraft must follow geodesics through curved spacetime, but the curvature changes over time as cosmic mass distribution evolves. The mathematical complexity of calculating geodesics through time-varying curved spacetime exceeds any conceivable computational capability. Quantum mechanical effects create additional navigation uncertainties that become significant over intergalactic scales and timescales. The Heisenberg uncertainty principle limits the precision with which position and momentum can be simultaneously determined. These quantum uncertainties, negligible for everyday applications, accumulate over million-year journeys to create position uncertainties larger than entire star systems. Dr. Roger Penrose's work on quantum gravity suggests that spacetime itself has quantum fluctuations at microscopic scales over intergalactic journey distances and times. These quantum fluctuations of spacetime geometry could accumulate into macroscopic navigation errors. The fabric of space through which spacecraft navigate is itself uncertain at the quantum level. The cosmic microwave background radiation creates navigation challenges due to its complex structure and evolution. The cosmic microwave background provides the closest thing to an absolute cosmic reference frame, but its temperature variations change over cosmic time due to the integrated history of cosmic structure formation. Navigation systems based on cosmic microwave background mapping would become increasingly inaccurate over million-year journeys. Dark energy and dark matter create navigation problems because their distribution and effects are poorly understood. Dark energy drives cosmic expansion, but might have spatial variations that affect expansion rates differently in different regions. Dark matter creates gravitational lensing effects that distort the apparent positions of distant objects. Both dark energy and dark matter can create navigation errors that accumulate over intergalactic distances. The observational horizon problem makes target identification increasingly difficult as cosmic expansion carries distant galaxies beyond observable limits. Galaxies that are visible when intergalactic journeys begin might disappear beyond the cosmic horizon during travel, times measured in millions of years. Navigating toward invisible, unobservable targets becomes meaningless. Dr. Max Tegmark's studies of cosmic horizon evolution show that future observers will see increasingly empty skies as cosmic expansion carries galaxies beyond observable distances. Intergalactic navigation faces the peculiar problem that target galaxies might cease to exist in any observable sense during journey times, making the concept of navigation toward disappeared targets philosophically meaningless. Magnetic field navigation, useful for planetary and interplanetary travel, becomes useless for intergalactic navigation because galactic magnetic fields are weak and change over cosmic timescales. The interstellar and intergalactic magnetic fields provide no reliable navigation reference because their structure evolves as cosmic plasma flows and stellar processes change the distribution of cosmic magnetic fields. Pulsar navigation, proposed for interstellar travel, fails for intergalactic journeys because pulsar signals become too weak to detect across intergalactic distances. Pulsars also evolve over million-year timescales, changing their pulse characteristics in ways that make them unreliable as navigation beacons for intergalactic travel. The navigation nightmare reveals that intergalactic travel faces not just engineering challenges but fundamental impossibilities related to the dynamic, evolving nature of cosmic structure. The universe changes too rapidly and chaotically for any navigation system to predict target locations across the million-year timescales required for intergalactic travel. Understanding these navigation barriers shows that intergalactic travel would be impossible even with unlimited energy, perfect propulsion systems, and ideal spacecraft design. The basic problem of knowing where to go and how to get there cannot be solved for journeys across expanding space over cosmic timescales. Navigation impossibility represents another absolute barrier that no conceivable technology can overcome. Chapter 8. Human Fragility. Perhaps the most sobering barrier to intergalactic travel is the fundamental incompatibility between human biology and the extreme environments, timescales, and isolation required for intergalactic journeys. Our bodies and minds evolve for life on planetary surfaces over timescales measured in decades, not for survival in the cosmic void over timescales measured in millions of years. Understanding human biological and psychological limitations reveals why intergalactic travel would destroy the very humanity it aims to preserve and transport. The cosmic radiation environment between galaxies represents an immediate and insurmountable threat to human life. Space beyond planetary magnetic fields is flooded with high-energy cosmic rays, solar particle radiation, and gamma rays that cause devastating biological damage. Dr. Eugene Parker's studies of cosmic ray environments show that radiation levels in interstellar space exceed lethal doses within months of exposure. In the void between galaxies, where cosmic ray shielding from stellar magnetic fields is minimal, radiation levels would be even more deadly. Cosmic rays consist of high-energy protons, alpha particles, and heavier atomic nuclei traveling at substantial fractions of light speed. When these particles strike human tissue, they create cascades of secondary radiation that damage DNA, destroy cellular structures, and cause cancers, genetic mutations, and organ failures. Current spacecraft shielding provides minimal protection against cosmic ray bombardment over interplanetary timescales. Extending this protection to intergalactic timescales would require shielding masses that exceed spacecraft payload capacity. Dr. Francis Cucinoda's research for NASA reveals that cosmic ray exposure during long-duration space missions creates cancer risks that exceed acceptable limits within a few years of exposure. For intergalactic journeys lasting millions of years, cosmic ray exposure would guarantee multiple lethal cancers, genetic damage severe enough to prevent reproduction, and neurological damage that would destroy cognitive function. No conceivable biological system could survive such radiation environments. The psychological challenges of intergalactic travel transcend anything humans have ever experienced. Million-year journey times exceed the entire span of human species' existence by factors of 10. No human psychology has evolved to cope with timescales where personal lifespans represent insignificant fractions of total mission duration. The psychological concept of journey becomes meaningless when travel time exceeds the evolutionary timescales of entire species. Dr. Jack Stuster's studies of isolation psychology in extreme environments show that humans begin experiencing severe psychological stress within months of complete isolation from human civilization. Antarctic research stations, submarine deployments, and space missions all reveal consistent patterns of psychological deterioration when humans are cut off from normal social contact. Intergalactic travel would impose isolation so complete and permanent that it would destroy the psychological foundations of human consciousness. The social isolation of intergalactic travel goes beyond mere physical separation to include temporal and cultural isolation that severs all connections to human civilization. Communication with Earth involves million-year delays that make meaningful contact impossible. By the time travelers receive messages from Earth, the civilizations that sent those messages would have evolved beyond recognition. Intergalactic travelers would experience the ultimate form of solitary confinement, isolation not just from other people, but from humanity itself. Recent research in social psychology reveals that human consciousness and identity are fundamentally social constructs that require ongoing interaction with other humans for maintenance. Prolonged isolation leads to loss of language skills, deterioration of social reasoning, and eventual breakdown of personal identity. Intergalactic travelers would experience isolation so extreme it would gradually erase their humanity, leaving them psychologically disconnected from the species they represent. The generational aspects of intergalactic travel create unprecedented biological and social challenges. Million-year journeys would encompass thousands of human generations born and raised entirely within spacecraft environments. These spaceborne populations would have no direct connection to Earth, no experience of planetary environments, and no understanding of the human civilization that initiated their journey. After a few generations, the concept of returning to Earth would become as alien to them as returning to the ocean is to land-dwelling mammals. Dr. Kim Stanley Robinson's studies of generational spacecraft psychology predict that multi-generational space populations would develop fundamentally different cultures, languages, and worldviews from Earth-based humanity. After thousands of generations in the artificial environment of intergalactic spacecraft, these populations would essentially become different species. Humans adapted to cosmic travel, but no longer recognizable as the humanity that began the journey. The biological challenges of reproduction and development in space environments make long-term human survival during intergalactic travel questionable. Microgravity environments cause bone density loss, muscle atrophy, cardiovascular deterioration, and immune system dysfunction. Current understanding suggests that human reproduction in zero gravity faces severe complications that might prevent successful multi-generational survival in space. Dr. Scott Kelly's year-long space mission revealed significant genetic changes, bone density loss, and vision problems that persist even after returning to Earth gravity. Extrapolating these effects to million-year timescales suggests that spaceborne human populations would undergo evolutionary changes so dramatic they would no longer be biologically compatible with Earth-based humanity. Intergalactic travel would create speciation events that divide humanity into separate evolutionary branches. The closed ecosystem requirements for intergalactic spacecraft create biological challenges that no technology can solve completely. Human survival requires complex ecological systems, including atmosphere recycling, water purification, food production, waste processing, and maintenance of genetic diversity in both human and supporting species populations. Maintaining these systems over million-year timescales requires ecological stability that no closed system has ever achieved. Dr. John Allen's studies of closed ecological systems, including the Biosphere 2 experiment, reveal that maintaining stable ecosystems in artificial environments is extraordinarily difficult, even over timescales of years. Ecological collapse, species extinctions, and atmospheric imbalances plague all attempts to create self-sustaining closed ecosystems. Scaling these systems to support human populations over millions of years approaches biological impossibility. The genetic diversity problem creates additional biological barriers to long-term human survival during intergalactic travel. Small populations suffer from genetic bottlenecks that lead to inbreeding depression, loss of genetic variability, and eventual population collapse. Maintaining genetically viable human populations requires minimum population sizes that exceed the capacity of any conceivable spacecraft. Population genetics models suggest that maintaining genetic diversity in isolated human populations requires thousands of breeding individuals. Dr. Cameron Smith's calculations for generation ship populations show that genetic viability requires spacecraft carrying at least 10,000 people with carefully managed breeding programs to prevent inbreeding depression. The life support requirements for such populations exceed any realistic spacecraft design capability. The medical care challenges for million-year intergalactic journeys exceed all possibility of solution. Spacecraft populations would face diseases, injuries, genetic disorders, and medical emergencies that require surgical intervention, pharmaceutical treatments, and medical technologies that must be maintained and updated over cosmic timescales. Medical systems reliable enough for million-year operation would require industrial medical infrastructure that exceeds spacecraft capacity. Dr. Virginia Watering's studies of space medicine reveal that even routine medical care in space environments faces extraordinary challenges due to equipment limitations, supply constraints, and the physiological effects of microgravity on medical procedures. Providing comprehensive medical care for thousands of people over millions of years would require mobile hospitals with pharmaceutical manufacturing, surgical facilities, and diagnostic equipment that no space mission could reasonably carry. The aging and death problem creates psychological and practical challenges unique to intergalactic travel. Unlike Earth-based human societies, intergalactic spacecraft populations would have no connection to eternal cycles of nature, planetary environments, or cultural institutions that give meaning to human mortality. Death in the void between galaxies lacks the contextual meaning that makes human mortality psychologically acceptable. Recent studies of thanatology, the psychology of death and dying, show that humans cope with mortality through connections to enduring institutions, natural cycles, and cultural legacy. Intergalactic travelers would face death in ultimate isolation, with no possibility of burial in familiar soil, no connection to continuing human civilization, and no assurance that their sacrifices serve any meaningful purpose. The evolutionary pressure problem suggests that human populations during intergalactic travel would face selection pressures completely different from those that shaped human evolution. The artificial environment of spacecraft, the cosmic radiation exposure, the psychological stresses of isolation, and the requirements for technical skills would favor genetic variants adapted to space travel rather than planetary life. Over thousands of generations, these selection pressures would create human subspecies adapted for cosmic travel, but increasingly incompatible with planetary life. By the time intergalactic travelers reach their destination, they might be biologically incapable of surviving on planetary surfaces. The journey would transform humanity into something entirely different from what began the voyage. Understanding human fragility reveals that intergalactic travel faces not just technological and physical barriers, but fundamental incompatibilities with the biological and psychological nature of humanity itself. The very characteristics that make us human, our social nature, our planetary adaptations, our psychological connection to Earth-based environments, make us unsuited for survival during intergalactic journeys. Human fragility represents perhaps the most personal and immediate barrier to intergalactic travel, forcing us to confront the possibility that cosmic exploration might require abandoning our humanity entirely. The biological and psychological costs of intergalactic travel would be so severe that successfully reaching another galaxy would represent the death of human nature rather than its expansion into the cosmos. Chapter 9. Technological walls. Beyond the biological and navigational challenges lies a series of absolute technological barriers that make intergalactic travel impossible, regardless of future scientific advances. These aren't limitations waiting for clever engineering solutions. They're fundamental constraints imposed by the laws of physics, thermodynamics, and information theory that no conceivable technology can overcome. Understanding these technological walls reveals why intergalactic travel will remain impossible, even for civilizations millions of years more advanced than our own. The materials science barrier creates the first insurmountable technological wall. Intergalactic spacecraft must survive cosmic radiation, thermal cycling, mechanical stresses, and chemical degradation over million-year timescales while maintaining structural integrity and functional capability. No material has ever been tested over such timescales, and the fundamental physics of atomic structure suggests that no material could survive intact for such periods. Dr. Arthur Ashkin's Nobel Prize-winning work on optical trapping reveals that individual atoms and molecules undergo continuous thermal motion that gradually breaks down all chemical bonds and crystal structures over sufficient time. Million-year exposures to cosmic environments would cause atomic migration, crystal defect accumulation, and molecular dissociation that would gradually disintegrate any spacecraft structure regardless of initial material properties. The cosmic radiation environment imposes additional materials constraints that no technology can solve. High-energy cosmic rays create displacement damage in crystal structures, causing swelling, embrittlement, and eventual mechanical failure of all materials. Dr. Lynn Mansour's studies of radiation damage in nuclear reactors show that materials suffer catastrophic property changes after exposure to radiation doses far smaller than those encountered during intergalactic journeys. Current understanding of radiation damage mechanisms suggests that any material exposed to intergalactic cosmic ray environments for millions of years would undergo structural changes so severe that its original properties would be completely lost. Metals become brittle, polymers decompose, ceramics crack, and even diamond develops defects that destroy its structural integrity. No conceivable material science advance can overcome these fundamental radiation damage processes. The reliability engineering barrier creates another absolute technological wall. Complex systems fail at rates determined by the reliability of their individual components. For spacecraft systems operating over million-year timescales, even components with extremely high reliability would accumulate failures that guarantee system collapse. The mathematics of reliability engineering proves that no complex technological system can operate reliably over cosmic timescales. Dr. Dmitry Kiselychoglu's pioneering work in reliability engineering established that system. Reliability decreases exponentially with time and component count. For spacecraft with millions of components operating over millions of years, the probability of system survival approaches zero regardless of individual component reliability. Even components with failure rates of 1 per billion years would accumulate enough failures to destroy spacecraft functionality over million-year missions. The redundancy solutions that improve reliability for shorter missions become counterproductive for intergalactic timescales. Adding backup systems increases system complexity, which increases overall failure rates faster than redundancy improves reliability. The mathematics of complex system reliability creates a fundamental trade-off where adding more backup systems eventually makes the overall system less reliable rather than more reliable. Recent advances in quantum computing reveal additional technological barriers related to information processing and storage over cosmic timescales. Quantum systems are inherently fragile, requiring isolation from environmental disturbances that become impossible to maintain over million-year periods. Classical computing systems suffer from bit flip errors caused by cosmic radiation that accumulate to destroy stored information over extended periods. Dr. John Preskill's work on quantum error correction shows that maintained quantum information requires continuous error correction processes that consume enormous amounts of computational resources. For quantum computers operating over million-year timescales, the error correction overhead would exceed the computational capacity available for actual mission functions. Classical computers face similar but less severe information degradation problems. The manufacturing and maintenance barrier creates technological walls that no automation can overcome. Intergalactic spacecraft must carry complete manufacturing capability to produce replacement parts, repair damage, and maintain systems over million-year operational periods. The industrial infrastructure required for such manufacturing capability would exceed the mass and complexity budgets available for any spacecraft design. Dr. Klaus Lackner's studies of self-replicating manufacturing systems reveal that complete industrial capability requires mining, refining, manufacturing, assembly, and quality control systems that scale with the complexity of products being manufactured. Spacecraft capable of manufacturing their own replacement components would require industrial systems more complex than the spacecraft they're designed to maintain. The artificial intelligence barrier compounds the manufacturing and maintenance problems because million-year missions require autonomous systems capable of learning, adapting, and making complex decisions without human oversight. Current AI systems are specialized for narrow domains and require continuous human guidance for complex problem-solving. The general artificial intelligence required for autonomous intergalactic missions remains beyond current technological capability despite decades of research. Dr. Stuart Russell's work on AI safety reveals that creating artificial intelligence systems reliable enough for autonomous operation over million-year timescales faces fundamental theoretical obstacles. AI systems must be capable of handling every possible contingency without human guidance while maintaining goal stability and operational coherence over timescales that exceed human comprehension. The energy storage and generation barrier creates additional technological impossibilities. Million-year missions require power generation systems that operate reliably across cosmic timescales while providing sufficient energy for propulsion, life support, manufacturing, and system maintenance. No energy generation technology has ever operated reliably for even tiny fractions of the required timescales. Nuclear fission reactors face fuel depletion and neutron-induced material degradation that limits operational lifetimes to decades. Fusion reactors, if they become practical, would face similar material degradation and fuel supply challenges. Solar power systems degrade under cosmic radiation and micrometeorite impacts over much shorter timescales than required for intergalactic missions. Dr. John Rather's studies of space power systems revealed that even the most optimistic projections for advanced power generation technologies suggest operational lifetimes measured in centuries, not millions of years. The fundamental physics of energy conversion processes creates degradation mechanisms that no technology can eliminate completely. The communication technology barrier makes maintaining contact with Earth impossible over intergalactic distances and timescales. Radio signals suffer from inverse square law power reduction, cosmic background noise, and interference from interstellar plasma that make long-distance communication extremely difficult. The power requirements for transmitters capable of sending detectable signals across intergalactic distances exceed reasonable spacecraft power budgets. Dr. Frank Drake's calculations for interstellar communication show that maintaining radio contact across galactic distances requires enormous antenna systems and power levels that challenge current engineering capability. Scaling these requirements to intergalactic distances creates communication challenges that exceed any conceivable technology solution. The data storage barrier creates information preservation challenges that no technology can solve completely. Million-year missions must preserve navigation data, operational procedures, cultural information, and scientific knowledge across timescales that exceed the operational lifetime of any information storage technology. Magnetic storage suffers from data decay, optical storage degrades under radiation exposure, and quantum storage requires continuous error correction. Recent studies of long-term data preservation reveal that no current storage technology can reliably preserve information for even thousands of years without active maintenance and data refreshing. The million-year data preservation requirements for intergalactic missions exceed all technological capability by factors of thousands. The systems integration barrier creates technological challenges that grow exponentially with mission, complexity, and duration. Intergalactic spacecraft require integration of propulsion, power, life support, navigation, communication, manufacturing, and AI systems that must operate together flawlessly over million-year periods. The complexity of such integration exceeds any engineering project ever attempted. Dr. Barry Boehm's studies of complex system development reveal that integration complexity grows exponentially with the number of interacting subsystems. The failure modes and interaction effects for systems as complex as intergalactic spacecraft become impossible to predict, test, or verify using any conceivable development methodology. The technology evolution barrier creates the ultimate technological impossibility. Technology advances so rapidly that any intergalactic mission launched today would be obsolete before it completed its journey. The spacecraft would represent million-year-old technology attempting to accomplish missions that home civilizations could achieve more easily using technologies developed during the mission's flight time. Moore's law and similar technological progress trends suggest that technology advances by factors of millions to billions over century-long timescales. Over million-year timescales, technological advancement would create capabilities so far beyond current understanding that intergalactic travel might become trivial using methods we cannot currently imagine or impossible for reasons we cannot currently understand. Understanding technological walls reveals that intergalactic travel faces not just current technical limitations, but fundamental barriers that no conceivable technological advancement can overcome. The laws of physics, chemistry, and engineering create absolute limits on technological capability that apply regardless of how advanced civilizations become. These technological walls operate independently of all other barriers to intergalactic travel. Even with unlimited energy, perfect navigation, and ideal human solutions, the fundamental technological challenges would still make intergalactic travel absolutely impossible. The universe has designed itself with technological barriers that ensure permanent galactic isolation regardless of how clever or advanced intelligence becomes. Chapter 10. Cosmic Loneliness. As we examine all the barriers to intergalactic travel together, the impossible distances, expanding space, energy requirements, timescales, speed limits, fuel needs, navigation challenges, human limitations, and technological walls, a profound and disturbing pattern emerges. The universe appears deliberately designed to isolate every galaxy from every other galaxy, ensuring that consciousness, intelligence, and life remain forever trapped within their cosmic birthplaces. This isn't merely an engineering challenge. It's a fundamental feature of reality that guarantees cosmic loneliness for all intelligence throughout the universe. The mathematical precision of these barriers suggests they aren't accidental limitations that might be overcome with sufficient cleverness or technological advancement. Instead, they appear to be fundamental design features of spacetime itself. The speed of light, the expansion rate of space, the energy requirements for acceleration, and the timescales involved all conspire with mathematical precision to create absolute barriers that no conceivable intelligence can overcome. Dr. Enrico Fermi famously posed the question that bears his name. If the universe should be teeming with intelligent life, where is everybody? The Fermi paradox has generated dozens of proposed solutions, from self-destruction scenarios to zoo hypotheses to rare Earth arguments. But understanding the impossibility of intergalactic travel suggests a simpler and more disturbing answer. Everybody is trapped in their own galaxy, as isolated from cosmic contact as we are. The isolation isn't temporary or technological, it's permanent and fundamental. Every intelligent species that has ever evolved in any galaxy throughout cosmic history faces exactly the same impossible barriers that we've explored. The laws of physics apply uniformly throughout the universe, meaning that alien civilizations millions of years more advanced than ours still cannot overcome the fundamental limitations of cosmic expansion, energy requirements, and timescales that make intergalactic travel impossible. This cosmic isolation creates what cosmologists call the galactic zoo hypothesis. Not that we're being observed by advanced aliens, but that every galaxy in the universe functions as an isolated preserve for consciousness, forever cut off from contact with other galactic preserves. Each galaxy contains its own unique evolutionary experiments in consciousness and intelligence. But these experiments must unfold in permanent isolation from all others. Dr. Frank Tipler's calculations of cosmic evolution suggest that this isolation might be intentional rather than accidental. The fundamental constants of physics, the speed of light, the expansion rate of space, the strength of gravity, the mass of elementary particles appear fine-tuned not just to allow stars, planets, and life to exist, but to ensure that life remains isolated within individual galaxies. The universe seems designed for beauty, complexity, and consciousness, but not for cosmic conquest or galactic communication. Recent observations of cosmic evolution support this isolation hypothesis. The accelerating expansion of space driven by dark energy means that galactic isolation will become more extreme over time. Galaxies beyond our local group are already receding at velocities that approach the speed of light, making them causally disconnected from our cosmic neighborhood. Future observers will inherit an increasingly empty universe where evidence of other galaxies gradually disappears beyond observable horizons. The psychological impact of permanent cosmic isolation challenges humanity's deepest assumptions about our place in the universe. We evolved as social creatures who solve problems through communication, cooperation, and shared knowledge. The possibility that consciousness throughout the cosmos is destined for permanent isolation contradicts our fundamental social nature and our hopes for cosmic connection. This isolation means that the great questions about life, consciousness, intelligence, and meaning must be answered independently by every galaxy in the universe. There will be no cosmic congress of civilizations sharing knowledge, no galactic federation solving problems through cooperation, no universe-spanning culture that unifies intelligent species across cosmic scales. Each galactic island of consciousness must explore these questions alone, without guidance or contact from other cosmic intelligences. Dr. Carl Sagan often spoke of the universe as a cosmos rather than a chaos, an ordered, knowable system where intelligence could eventually understand and explore all of reality. But cosmic isolation suggests that the universe is designed more like a vast library where each galaxy contains a single book, and no reader can ever access books from other galaxies. The cosmic library is infinite, but each reader is confined to a single volume for all eternity. The implications extend beyond astronomy and physics to philosophy and meaning. If every intelligent species in the universe faces permanent galactic isolation, then cosmic evolution becomes not a story of expanding knowledge and connection, but a story of eternal separation and independent development. Each galaxy becomes a cosmic monastery where consciousness develops in isolation from all other forms of awareness. This monastic model of cosmic consciousness suggests that the universe values diversity over unity, individual development over collective knowledge, unique evolutionary experiments over standardized solutions. Each galaxy develops its own approaches to consciousness, intelligence, technology, and meaning without contamination or guidance from other galactic experiments in awareness. The accelerating cosmic expansion driven by dark energy makes this isolation increasingly absolute over time. Dr. Lawrence Krauss's calculations show that future observers will see increasingly empty skies as galaxy after galaxy disappears beyond the cosmic horizon. Eventually, only the local group will remain observable, and even these nearby galaxies will become increasingly isolated as space expansion overwhelms their gravitational binding. This temporal evolution of isolation means that consciousness in our cosmic era enjoys maximum cosmic awareness. We can observe billions of other galaxies and contemplate the vast scope of cosmic intelligence, even though we can never contact it. Future cosmic eras will be lonelier, with consciousness developing in apparently empty universes where evidence of other galaxies has been erased by cosmic expansion. The loneliness becomes even more poignant when we consider that intelligence might be rare within individual galaxies as well. If consciousness requires unlikely combinations of circumstances to evolve, stable planetary environments, appropriate chemical compositions, protection from cosmic catastrophes, sufficient evolutionary time, then most galaxies might contain only one or a few intelligent species. Galactic civilizations might be as isolated within their galaxies as galaxies are isolated within the cosmos. Dr. Nick Bostrom's work on existential risk suggests that advanced civilizations face numerous potential extinction events that might prevent them from achieving galactic-scale presence. Nuclear war, environmental collapse, artificial intelligence risks, asteroid impacts, gamma-ray bursts, and other catastrophes could destroy civilizations before they spread beyond their home planets. Galactic isolation might be compounded by planetary isolation within galaxies. The temporal dimension of cosmic isolation adds another layer of loneliness. Even if other intelligent species exist within our galaxy, they might have evolved millions of years ago and gone extinct. Or they might evolve millions of years in the future after our own extinction. Consciousness might be isolated not just spatially but temporally, with different species missing each other across the vast time scales of cosmic evolution. Recent studies of the galactic habitable zone suggest that stellar formation rates, heavy element abundances, and cosmic catastrophe frequencies change over cosmic time in ways that make intelligence more likely during certain epochs. We might be living during a brief cosmic moment when intelligence is possible, surrounded by vast temporal deserts when consciousness cannot exist. The cosmic microwave background radiation provides a haunting reminder of our temporal isolation. This ancient light preserves information about the universe's condition when it was only 380,000 years old. Long before the first stars formed, before galaxies condensed, before any possible consciousness could exist. We see evidence of a universe that existed for vast periods before consciousness was possible. And we can predict a future universe that will exist for vast periods after consciousness becomes impossible. Understanding cosmic loneliness forces us to confront the possibility that consciousness in the universe is intrinsically tragic, destined for isolation, prevented from cosmic connection, confined to brief islands of awareness in an infinite ocean of empty space and time. Each thinking being throughout the cosmos experiences the same fundamental loneliness, the same cosmic isolation, the same unrequited longing for connection with other forms of consciousness. This cosmic loneliness might be the price of consciousness itself. Perhaps awareness requires isolation to develop unique perspectives, individual insights, and diverse approaches to understanding reality. Perhaps cosmic contact would homogenize consciousness throughout the universe, destroying the diversity of awareness that makes consciousness valuable and meaningful. The design of cosmic isolation might reflect a deeper wisdom about the nature of consciousness and meaning. Instead of creating a universe where intelligence can merge into cosmic unity, the universe appears designed to preserve the individuality and uniqueness of every conscious entity. Every intelligent species, every galactic civilization. We are alone not as punishment or accident, but as the necessary condition for consciousness to explore the infinite possibilities of awareness. Cosmic loneliness becomes not just our fate, but our defining characteristic as conscious beings in an isolated universe. We are the universe's way of experiencing loneliness, of contemplating isolation, of finding meaning despite permanent separation from other forms of consciousness. Our cosmic solitude makes our individual consciousness more precious rather than less meaningful. Chapter 11. Ultimate Perspective. After exploring every conceivable barrier to intergalactic travel, we arrive at a profound realization that transcends physics, engineering, and technology. The impossibility of reaching other galaxies reveals something fundamental about the nature of existence itself. We are not prisoners of technical limitations or temporary constraints. We are inhabitants of a universe, deliberately designed to preserve cosmic mystery, individual growth, and the irreplaceable value of local consciousness. Understanding our galactic confinement opens our eyes to truths about reality that no amount of cosmic travel could ever reveal. The barriers we've examined, distance, expansion, energy, time, speed limits, fuel requirements, navigation impossibilities, human fragility, and technological walls, combine with mathematical precision to create absolute cosmic isolation. This isn't a series of unfortunate coincidences that clever engineering might overcome. It's a fundamental architecture of reality where every physical law, every cosmic constant, every relationship between matter, energy, space, and time conspires to keep galactic civilizations forever separated. This precision suggests intentionality rather than accident. The universe appears designed to be simultaneously infinite in scope and absolutely limited in accessibility. We can observe billions of galaxies through our telescopes, contemplate vast cosmic processes through our physics, and imagine countless forms of intelligence throughout the cosmos through our mathematics. But we can never visit, never contact, never directly experience any reality beyond our galactic neighborhood. Dr. Brandon Carter's anthropic principle reveals that the fundamental constants of physics must fall within narrow ranges that allow complexity and consciousness to exist. The speed of light, the expansion rate of space, The strength of gravity and the mass of elementary particles all have values that permit stars to shine, planets to form, and life to evolve. But these same precisely tuned constants also ensure that consciousness remains isolated within individual galaxies. This suggests that cosmic isolation isn't an unfortunate side effect of physical laws designed for other purposes. It might be a primary feature of reality's design. The universe appears optimized not for cosmic conquest or galactic communication, but for the development of unique, isolated forms of consciousness that must confront the deepest questions of existence without external guidance or cosmic collaboration. The implications transform our understanding of humanity's cosmic role. Instead of being explorers destined to spread across the universe, we are cosmic witnesses whose purpose is to observe, understand, and contemplate the vast reality that surrounds us but remains forever beyond our reach. Our isolation makes our consciousness more precious, not less significant, because we represent the universe's unique perspective from this particular location and time. Consider what this means for the search for meaning in an apparently meaningless cosmos. Traditional approaches to cosmic meaning often assume that significance comes from expansion, conquest, and connection, that consciousness becomes meaningful through contact with other forms of awareness and through physical exploration of cosmic reality. But cosmic isolation suggests that meaning emerges through depth rather than breadth, through intensive understanding of local reality rather than extensive exploration of distant realms. The mathematical beauty of cosmic isolation reveals that consciousness might be designed for contemplation rather than conquest. Every galaxy in the universe contains sufficient complexity to support infinite intellectual and spiritual exploration. The Milky Way alone contains 400 billion stars, potentially trillions of planets, countless cosmic phenomena, and enough physical, chemical, and biological complexity to occupy consciousness for billions of years of investigation and understanding. Dr. Freeman Dyson's calculations of information content in cosmic systems suggest that a single galaxy contains more information than any intelligence could process in cosmic lifetimes measured in trillions of years. The complexity available for exploration within our galactic prison exceeds the processing capacity of consciousness by factors so enormous that cosmic isolation becomes irrelevant to the search for knowledge and understanding. This abundance of local complexity suggests that cosmic travel might be unnecessary for cosmic understanding. The deepest truths about reality, the nature of consciousness, the meaning of existence, the relationship between mind and cosmos might be fully accessible through intensive study of local reality rather than extensive exploration of distant regions. The universe might be designed so that every location contains complete information about cosmic truth. Recent developments in holographic principle physics support this idea that complete cosmic information might be accessible from any location. If the three-dimensional universe we experience is a projection of information stored on distant boundaries, then every region of space contains complete information about cosmic reality. Traveling to distant galaxies wouldn't reveal new information. It would only show us different projections of the same holographic cosmic truth. The eternal nature of cosmic isolation also transforms how we understand time and meaning. Instead of viewing our cosmic epoch as a brief moment before humanity spreads across the universe, we can recognize it as the entire span of meaningful human existence. Our descendants will face the same cosmic isolation for billions of years until the sun exhausts its fuel and Earth becomes uninhabitable. Cosmic isolation isn't a temporary condition waiting to be overcome. It's the permanent context for all human existence throughout all conceivable time. This permanence suggests that meaning must be found within the conditions of isolation rather than through escape from isolation. Cosmic meaning comes not from transcending our limitations, but from fully embracing and exploring the infinite possibilities available within those limitations. We are not cosmic prisoners waiting for release. We are cosmic gardeners cultivating consciousness within the boundaries of our galactic preserve. The philosophical implications extend to questions about death and transcendence. Traditional cosmic optimism often promises that consciousness will eventually spread throughout the universe, achieving a form of cosmic immortality through physical expansion. But cosmic isolation suggests that consciousness is inherently finite and local, achieving transcendence through depth of understanding rather than breadth of expansion. This localized transcendence might be more meaningful than cosmic expansion. Instead of spreading consciousness thinly across vast cosmic distances, cosmic isolation concentrates consciousness within regions where it can achieve maximum depth and intensity. Every galaxy becomes a cosmic monastery where consciousness develops without distraction from external influences, achieving purity of insight impossible in a cosmically connected universe. Dr. Teilhard de Chardin's concept of the noosphere, a global network of consciousness that eventually transcends individual intelligence, might apply at galactic scales rather than cosmic scales. Our galaxy might be evolving toward a form of galactic consciousness that integrates all intelligence within the Milky Way while remaining isolated from consciousness in other galaxies. This galactic noosphere would achieve cosmic awareness without requiring cosmic travel. The isolation also suggests that cosmic diversity is more valuable than cosmic unity. If all galaxies could communicate and share information, consciousness throughout the universe might converge towards similar solutions, similar worldviews, and similar approaches to existence. Cosmic isolation preserves the diversity of consciousness by ensuring that each galaxy develops unique perspectives on reality without contamination from other galactic viewpoints. This diversity of isolated galactic consciousness might be the universe's way of exploring all possible approaches to awareness and understanding. Each galaxy becomes a cosmic laboratory for consciousness, developing different solutions to the problems of existence, different approaches to meaning, and different relationships between mind and reality. The universe achieves maximum exploration of consciousness possibilities through isolation rather than through connection. Understanding our ultimate cosmic perspective reveals that the impossibility of intergalactic travel isn't a limitation to be overcome, but a design feature to be appreciated. We exist in a universe crafted with perfect precision to support consciousness while preventing cosmic conquest, to enable awareness while preserving cosmic mystery, to allow observation while maintaining eternal wonder. Our galactic isolation makes every moment of consciousness more precious because it's unrepeatable and irreplaceable. Every human thought, every scientific discovery, every artistic creation, and every moment of love or understanding represents a unique cosmic event that will never occur anywhere else in the universe. Our thoughts and experiences aren't just local phenomena. They're unique cosmic treasures that add irreplaceable value to the universe's exploration of its own possibilities. The ultimate perspective transforms cosmic loneliness from tragedy into gift. We are alone in the cosmos, not as punishment or accident, but as the necessary condition for consciousness to achieve its deepest purpose, to serve as the universe's way of understanding itself from every possible perspective, in every possible location, through every possible form of awareness. In recognizing the impossibility of intergalactic travel, we discover the infinite possibility of galactic existence. We are not cosmic prisoners, but cosmic witnesses, not failed explorers, but successful consciousness, not isolated accidents, but essential participants in the universe's vast project of self-understanding through infinite forms of isolated, precious, irreplaceable awareness. Our cosmic situation becomes not a problem to be solved, but a mystery to be lived, not a limitation to escape, but a condition to explore, not a prison to break free from, but a garden to cultivate with infinite care, infinite wonder, and infinite appreciation for the cosmic gift of consciousness itself. Throughout this exploration of cosmic impossibility, we've discovered that the barriers to intergalactic travel aren't merely technical challenges waiting for future solutions. They're fundamental features of reality itself. The staggering distances that mock our fastest rockets, the expanding space that grows faster than we can travel, the energy requirements that exceed the output of stars, the timescales that transcend human comprehension, the speed limits built into spacetime, the fuel masses that dwarf planetary bodies, the navigation chaos of cosmic motion, the biological fragility that makes humans unsuitable for cosmic journeys, the technological walls that no engineering can overcome, and the cosmic loneliness that defines existence throughout the universe, all combine with mathematical precision to create absolute barriers that no intelligence can surmount. But perhaps the most profound discovery is that these barriers reveal the universe's deeper wisdom about consciousness and meaning. We are not failed cosmic explorers trapped by technological limitations. We are successful cosmic witnesses, designed to observe and understand the infinite mystery that surrounds us while remaining forever grounded in the local reality that gives our consciousness meaning and purpose. The impossibility of reaching other galaxies forces us to find cosmic significance in cosmic limitation. Instead of spreading thinly across unreachable distances, consciousness concentrates intensively within accessible boundaries. Instead of pursuing impossible dreams of cosmic conquest, awareness explores infinite possibilities of cosmic understanding. Instead of lamenting our galactic imprisonment, consciousness celebrates its irreplaceable role as the universe's way of understanding itself from this unique cosmic perspective. This perspective transforms how you understand your own existence in the cosmos. You are not a cosmic accident trapped on an insignificant planet in an unremarkable galaxy. You are a conscious entity experiencing reality from a viewpoint that has never existed before and will never exist again anywhere in the universe. Your thoughts, experiences, and understanding represent unique cosmic treasures that contribute irreplaceable value to the universe's vast project of self-awareness. When you look up at the night sky and see the faint light of Andromeda galaxy, remember that you're observing a realm as forever unreachable as yesterday or tomorrow. That galaxy contains hundreds of billions of stars, potentially countless forms of life and intelligence, and cosmic wonders beyond imagination. But it exists in permanent isolation from our reality, separated by barriers so absolute they're woven into the fabric of space-time itself. This unreachability doesn't diminish the wonder, it intensifies it. The cosmic mystery that surrounds us becomes more precious because it remains mysterious, more beautiful because it stays beyond our grasp, more meaningful because it preserves the diversity of consciousness that gives the universe its infinite richness of perspective and understanding. As you continue through your daily life after understanding these cosmic truths, carry with you the recognition that consciousness is the universe's most precious achievement precisely because it's rare, local, and isolated. Every moment of awareness, every flash of understanding, every experience of beauty or meaning represents a cosmic success story that required 13.8 billion years of cosmic evolution to achieve. And that adds irreplaceable value to reality itself. You are not separated from the cosmic process. You are the cosmic process, experiencing itself from the inside, understanding itself through your unique perspective, celebrating its own infinite mystery through your capacity for wonder. The barriers that prevent intergalactic travel aren't limitations on cosmic consciousness. They're the necessary conditions that make cosmic consciousness possible, meaningful, and infinitely precious. The universe has designed itself as a vast garden of isolated consciousness, where every galaxy nurtures unique forms of awareness in perfect solitude, where every thinking being experiences the irreplaceable gift of cosmic understanding from an absolutely unique perspective, where the infinite mystery of existence remains forever fresh, because it can never be completely explored or finally understood. We exist not as cosmic prisoners, but as cosmic gardeners, cultivating consciousness within the perfect boundaries that make awareness possible. Our galactic isolation isn't a limitation to overcome, but a design feature to appreciate. A cosmic gift that ensures consciousness remains forever mysterious to itself, forever capable of wonder, forever discovering new depths in the infinite reality that surrounds and sustains us. The recognition that other galaxies remain forever beyond our reach doesn't diminish our cosmic significance. It reveals that significance comes not from physical expansion, but from depth of understanding, not from conquering distance, but from comprehending meaning, not from escaping our cosmic situation, but from fully embracing the infinite possibilities available within our galactic home. Every star in our galaxy represents a potential sun for countless worlds. Every planet might harbor unique forms of life and consciousness. Every nebula, black hole, and cosmic phenomenon offers infinite opportunities for scientific discovery and spiritual contemplation. The Milky Way contains more complexity, more beauty, and more mystery than consciousness could explore in billions of lifetimes. We are not trapped in too small a space. We are gifted with more cosmic territory than we could ever fully appreciate. Our permanent galactic isolation also means that every human achievement becomes cosmically unique. Every work of art, every scientific discovery, every act of love, and every moment of understanding represents something that has never happened before anywhere else in the universe and will never happen again. Our thoughts and creations are not insignificant local phenomena. They are irreplaceable, cosmic events that add unique value to the universe's infinite project of self-exploration. The mathematics of cosmic impossibility transforms into the poetry of cosmic meaning. We cannot reach other galaxies precisely because consciousness is too precious to be diluted across impossible distances, too valuable to be wasted on unreachable destinations, too important to be distracted from the infinite mysteries available within our cosmic neighborhood. If you've journeyed this far through the exploration of cosmic impossibility and found yourself amazed by the universe's perfect design for consciousness and mystery, subscribe and give this video a thumbs up. The recognition that we can never reach other galaxies opens infinite possibilities for understanding our own cosmic neighborhood. Check out my video on what happens inside a black hole, exploring the cosmic mysteries we can study reveals wonders as profound as any we might find in unreachable galaxies. The question we began with, why is it impossible to reach another galaxy, has revealed itself to be an invitation to understand something far more profound than engineering limitations. It's a doorway to recognizing that consciousness is the universe's way of celebrating cosmic mystery rather than conquering it, and that our cosmic isolation is not a prison sentence, but a cosmic gift that makes every moment of awareness infinitely precious and eternally meaningful.